So good afternoon, everyone, those online and those who are in the room in person. So as you know, we are going to have our guest speaker today, and I can see him already joining us. So Akhil, thank you very much for calling in. I am going to introduce you first and also introduce the students to you before passing the floor to you. So as you know, this is a modeling course, primarily focused on hydrologic modeling with applications of model calibration, optimization, uncertainty analysis, sensitivity analysis, very much similar to your expertise and what you do in real world in practice. So Akhil, this gentleman, I've come to know him fairly recently, and interestingly, he told me yesterday that we met a few years back at AGU conference, American Geophysical Union, either in San Francisco or New Orleans or Washington, D.C. I'm not sure yet. But we kind of share some similar history. Of course, he's much younger than me. But he did his undergraduate degree in civil engineering in IIT Bombay, Indian Institute of Technology. And if you have never been to India, those are top universities in India, producing a lot of good civil engineers. And my understanding is he moved to Canada first as a Global Link MyTax intern. So as an international student, you can apply under MyTax, which is something federally funded in Canada, come to a Canadian university, do a bit of research during our undergraduate program, for example, and he did that at the University of Western Ontario. Then he moved to UBC, working with my colleague and friend, Stephen Weiss, who is working in fairly similar area of research to mine, hydrologic modeling, and also a lot of information theory, that sort of things. And what is impressive about Akhil Kumar is that he has some interesting, diverse work experience with multiple different institutions. Something I didn't know and learned this morning is that he worked with 𝗪𝗁𝗏, for example, which is world-leading, I guess, non-for-profit consulting service based in the Netherlands. I think in the Delft. Delft is a very famous city in Netherlands for water research, by the way. Akhil will correct me if I'm wrong. And working with some world-class researchers, for example, in the field of decision-making under deep uncertainty. And that's something that I mentioned very quickly yesterday. And anyway, so he's been working with different institutions until recently that he joined the city of Vancouver. I think he's been working there already for a couple of hours or a couple of years or more. And yeah, he's doing some interesting stuff in practice, fairly similar to what we're talking about here, but to address some real-world challenges about flooding issues. And of course, we're talking about the city of Vancouver. That's not only about fluvial, pluvial flooding, it's also about coastal flooding. So Akhil, before I pass it to you, I just want to make the students known to you. And I'm going to ask you, folks, if you could move forward a little bit so it can be captured in that camera so we can better connect. And also those online, if you could turn on your camera, at least for a few minutes, so you can see a few faces. Yeah, and Akhil, you know what? So this cohort, as I told you before, has a diverse background from engineering, natural sciences, and they've come to us with diverse background geographically as well, nationally and internationally. Yeah, quite a diverse group. Sometimes the discussion could be interesting because different people might provide different views, based on their lived experience in different countries before. Okay, I'm going to change this presentation tracking mode, turn it off for a second so you could see what's happening here. Okay, not working, that's fine. So yeah, I'm gonna quickly just walk around. By the way, this is we paid like, I don't know, 10, 20K for this camera. So it's equipped with AI, it just follows me like a TED Talk. Yeah, so I'm hoping that you can see that folks are sitting here. Good. So, Akhil, I'm turning it over to you. And yeah, thanks very much for joining us today. Very exciting to have you.
Good. Thank you so much. Thank you, Saman, and thanks for the warm introduction. And hi, students, everyone. Thank you so much for coming today and giving me this opportunity to share a bit about our work and share some interesting tips for you. You all have got a very good supervisor, good good instructor. He definitely knows a ton about hydrology, uncertainty, and all of that very practical tools. So definitely make use of that. That's how I would like to start first. Yeah, I won't go through my background and stuff because Saman has already covered it. I currently work at City of Vancouver. I'm a senior civil engineer. In my current portfolio, I lead the pump station planning work program, which has been established just last year only. And before that, I was doing mostly flood management related projects, some sewer infrastructure planning projects as well. Yeah, so I've got a slide deck for you all. Let me just pull up here. Where is it? Just give me a second. Okay, are you able to see my screen? Okay, good. Yeah, so for today, I picked an interesting topic. I hope that this will provide you some good insights on how we manage coastal flooding and extreme rainfall flooding in urban context specifically. I won't go into too much of the technical details, although it's necessarily for me to provide some of the background, but it's not going to be too technical heavy. And I hope I did a good job in making up a nice storyline around it. So hope you'll like it. Before I start my presentation, I'd like to do some land acknowledgement. The City of Vancouver acknowledges the unceded and ancestral territories of Musqueam, Squamish, and Tsleil-Waututh. We recognize they have been stewards of these lands since time immemorial, and their unique relations, title, and rights in these territories remain intact. As I said, I've got like a substantial slide deck, but I'll try to do a good job in explaining each of these points. So we'll start off from urban flood hazard mechanisms for about 15-20 minutes. I'll talk about coastal flood hazard, rainfall flood hazard, a combination of those, and how we and also providing a bit of the context about Vancouver, like what sort of issues we are having here and how it's been more challenging for us. Then it will connect me to compound flood hazard assessment. By compound, I mean combination or joint events. So this one I'll specifically talk about compound coastal and rainfall flood events and how we assess them, what sort of considerations are need to be taken care of, and also giving you, as I'll talk, I'll give you some tips and tricks as enter in different career paths moving forward. So I hope I'll give you a flavor of those as well as I speak. And lastly, I'll do some Q&A, and I promise someone that I'll reserve some extra time because I understand you may have some extra questions, in general questions about career paths or like typical life, work life in the city, for instance, those who are looking for this type of career. I also, did my research master's, so I come from that academic background and how I'm using my academic knowledge and in finding solutions to these practical problems. This could be a new lens for you, and I'm happy to take some questions in the end. Although I committed for 1 p.m., like for 1 hour total, but I can extend potentially for 15-20 minutes more. I won't mind. Before I jump into technical details, I thought to just give you a quick overview about myself. I think work is one thing, but what about life in general? And I like to see this from others as well. So, well, in a nutshell, this is me. I have different interests, different passions in life. I like to travel. As you can see here, I like to travel cheap, backpacking style. Don't want to carry these heavy luggages. And me and my wife, we both love traveling. So we often, whenever we get a chance, we do these backpacking style trips. Cooking and light music is relaxation exercise for me. I understand most of you won't enjoy cooking and find burdensome, especially as a student. But yeah, for me, I enjoy it honestly. When I'm on travels or at local places, I like to take photos as well. Just added a photo from my last year's trip in Switzerland, and the mountains, Alps, and the nature stuff gives me a lot of peace and calmness, and that's what I enjoy capturing. Also, I don't miss any opportunity in checking out water management infrastructure. So, for example, when I was in Netherlands, this 𝗪𝗁𝗿 pump station in Rotterdam, it's a must see. It's an incredible piece of engineering, what people had, done back in those days, and how they harnessed wind and power and water, and creating energy out of it, and solving the flooding issues, recreating land from ocean. There's a whole ton of incredible engineering work that Dutch folks have done. So yeah, whenever I go and I try to find these opportunities for learning. Speaking of learning, I try to try to find some time to read books, and try to myself keep updated on stuff on like health and mental peace, and like also AI, because everybody's crazy about AI these days. So I try to spend some more time in learning new skills as well. I practice yoga, meditation. I think that's been very useful for me. Um, yeah, without spending too much time on myself, let's talk about the actual project. So let's begin the presentation with urban flood hazard mechanisms, and also providing you Vancouver context. As most of you are familiar of, there are basically three types of mechanisms in urban context, right? So there's flooding that can happen because of excessive rain. And why does it happen? So because of high impervious areas, water cannot infiltrate in the ground. The soil gets saturated pretty quickly, so water has to find its way somewhere. It finds its way through catch basins, it finds its way through sewers, underground sewers, and ultimately to a water body. But what if there's excessive rainfall and the amount of runoff exceeds the infrastructure capacity? Water will flood out somewhere. So that's causing fluvial flooding. There's another type of flooding that can happen in urban areas resulting from the creeks or the rivers whenever there's excessive rainfall in the upper watershed, or if there is like a freshet, spring freshet can also cause excessive runoff. And if the water level exceeds the bank elevation, water has to find its way and finds the gravity, the low point, and cause flooding in residential areas typically. Coastal flooding is also an serious emerging flood mechanism, and most of you are familiar. I hope it's basically a combination of high tide and or storm surge, that exceeds basically the shoreline elevations, whatever infrastructure that you have down there, and can actually cause serious havoc. And a combination of these can also happen, and that's what I'm going to talk about: compound flooding. So that's another layer of flood mechanism. When we see the rainfall spectrum, broadly we see three types of rain, right? So we see light showers most of the times. Actually, I'm unsure about Saskatchewan climate. Sorry. The hydrology might be very different, but in Vancouver, it's a temperate rainfall climate, so it rains a lot, as you might have heard about. But we do get some sunny days. Today is such a very nice, beautiful sunny day, but we do get a lot of rain here. So this is actually speaking to Vancouver context. I should not generalize it. But yeah, most days we see the light showers, and moving on, we see some heavy rain. Then extreme storms are fairly rare, which you can fairly quantify it less than 10% of the time, right? What do we design? So how do we engineer the water management? So we pick up spectrum. So let's say we design our infrastructure for light rain to heavy rain, and we call it minor drainage system. And that includes, as I said, catch basins, some roof gutters, some underground pipes, and outfall structures, and so and so. The hope is that it will manage certain amount of the heaviness of the rainfall, as you can qualitatively imagine. In terms of the major drainage infrastructure that is supposed to service extreme storms, pipes are not in the game. Pipes are done. They are full. They're running full. They cannot carry more runoff. So water has to find its way. As I said, it finds its way on road, swales, streams get activated, and that's where we see the major water conveyance going through. Unfortunately, in Vancouver, we have lost the major conveyance because of the past historic actions. In the past, as I said, Vancouver was a temperate rainforest, and many streams used to flow in different parts of the city. The map on the left shows you, let me turn on my laser. Yeah. Many streams used to flow, as you can see here. Unfortunately, with urbanization, most of these streams were piped underground and we lost them. And right now, we only have a few surviving streams, which are shown in this blue color. So this is only a handful of streams that are surviving and providing some major conveyance during the extreme rainfall events. But otherwise, we see flooding on the street, which ends up, causing damage to the buildings, critical infrastructure assets, and so and so. In Vancouver, we also don't have, the standard drainage infrastructure as you can think of. So, for example, what we have here is a shoreline. If those who have been to Vancouver, you will recognize this, a seawall, which it's one of the gems of Vancouver. But it doesn't even provide any ecological benefit, right? It's a hard structure, hard wall, does not connect well to the environment, although it provides some flood protection as of now, but then maintaining and increasing it, adapting it to sea level rise has been a considerable challenge for us. And it does not even connect nicely with the internal drainage infrastructure. Well, in my later slides, I'll talk about. Whereas in other municipalities around us, they have got new infrastructure. They got pump stations which can pump out water from low lying to the ocean. They've got ditches that can also provide some storage. And this is not just a piece of excavation, right? It's actually an engineered infrastructure. The capacity, the size, the banks, elevation, the slopes, and everything. It's an engineered infrastructure and it's supposed to provide those storage. We don't have those, unfortunately. And as a result, we have been seeing a lot of severe consequences of not having those infrastructures. So, for example, I just listed a few significant rainfall events that happened in the last 4 or 5 years or so. The trend has been increasing. It's crazy. So starting off, let's say back in 2019, there was a 100-year return period event. I hope all of you are familiar with return period language because I'll be using this very often in my presentation slide. But basically an annual exceedance probability, the IDF, if you can recall. So, we have been seeing these significant events already. In our infrastructure, our sewers are designed for, let's say, 10-year or maybe max 25-year return period rainfall. So as I said, extreme rainfall, water has to find its way. It floods the streets, buildings, and people take out their kayaks, and it's crazy what's been happening in the last 5, 6 years. Not just in Vancouver, right? The last year, Toronto Union Station got flooded. It was a heavy atmospheric rainfall event. In Montreal, lots of damaged buildings and public assets got damaged too. And it's in the order of millions, seriously. So what does climate change mean for us? Climate change means more intense, short duration rainfall events. So like quick snap of rainfall, and then more likelihood of atmospheric river events. So atmospheric river, probably not the word that floats around in Saskatchewan, but in here in BC, it's basically like a low pressure system that brings moist, air, and then it condenses here in Vancouver because of the mountain climate, and it, you know, uh, provides that excessive precipitation. So we are already seeing the consequences of it. We are already seeing more and more increasing atmospheric river events, and there are some statistics here. I won't go into detail, but we have done some study. We have found that yes, the trend is likely going upward because of climate change. So that was all about rainfall. I'll go through some of the coastal basics first, because I understand this course did not cover so much on the coastal side, and some of you might have some background, great, but those who don't have it, I'll try to provide you some basics of it. So yeah, so basically, when you talk about coastal flood, there are different components to it. The first component here is astronomical tide. So astronomical tides are basically the result of the increase or decrease in water surface elevation, ocean elevation, because of the gravitational pull of the Earth, Sun, and Moon. The Sun and Moon, right, on the Earth. So that, and those are like fixed. You can predict astronomical tides for any future year. Like you can predict for 1,000 years in future what will be the astronomical tide in my city, because it's all math. You know how the planets have been evolving, their velocities, angular momentum, so and so you can predict them. In Vancouver, we see a huge range of tides. So every day we almost see like 4.5 meter of drop, and not many people pay attention to it, right? Every day it's significant increase, 4.5 meter, if you can imagine, right? It's a significant increase. Every day we see two high tides. So this one is the high tide, this one is high tide, and then we see two low tides. So this is the lowest one, and then this is the lower one. And this type of pattern where we have two different magnitudes of high tide and two different magnitudes of low tide, it's called mixed semi-diurnal tides. So in different parts of the world, this pattern is different. In some part of the world, the high tides actually match. There are no two high tides. There's only one high tide, one low tide, and there's a different term for it. But it depends in what location of the Earth you are in and what the gravitational pull is. Another component is storm surge. So storm surge, you might have heard a lot in the news. It's in simple words, is basically increase in water elevation above the predicted tide. And why it's happening is because there's low atmospheric pressure that builds up in the ocean, and that increases the ocean elevation. And when there is wind, it pushes this low pressure cell towards the shoreline. So if the low pressure system stays in the ocean, and if there is no wind, storm surge doesn't impact us as such. But only when there is wind, that's when we see the actual effect of it. So this is a graphic that I pulled from the December 27th, 2022 storm surge event. And so we are here, Vancouver is here. Pay attention to the red cell. The red cell means the low pressure. Pay attention to how it moves from ocean towards inland, and then how it will impact Vancouver. So I'll just play it. Why is it not allowing me to play? Oh, shit. Sorry, one sec. Okay. You see that? Let me do it again. So you will see so this one right here just slams to this area, right? So this is what is actually troublesome, and that's what increases the coastal elevation and impacts the coastal properties. Here's another short video that shows the king tide and one of the king tides that occurred in Vancouver. Don't know why it's not playing. Too bad. Should play automatically. 1 second. Anyway, too bad. Sorry. But then maybe you can, from the image, you can see that the waves are too high. So it was a perfect combination of everything, right? So it was king tide, which is the highest tide of the year, technically. And then there was storm surge, and then there was wind. So all three combinations actually further increased the coastal water level, and there was like huge waves and caused damage to the seawall, the wall along the ocean that I was showing earlier. So we have been already seeing these events occurring. So climate change causes sea level rise and warming ocean expands, glaciers melt, ice cap melt. So it definitely will increase the total ocean level. So in BC, British Columbia, we use this standard curve, which is like a policy guideline for coming from the province to design any coastal infrastructure for up to year 2100 and beyond. So essentially, this is in simple words. For example, based on the climate model outputs, we know what the trajectory will be. And because there's uncertainty in climate models, we have this band, high and low. So we know what the trajectory would be, and we take the median of that. So the relative sea level rise based on the year 2000, we are saying that for up to year 2100, we're designing for up to 1 meter of sea level rise. And that has been our set standard. Although this was done in 2011, we have been fairly using it, and we also use updated knowledge from IPCC reports if we have to update our projections. But that's going to make situation more worse, sea level rise. This is just a simple graphic to help you visualize how coastal flood impacts the properties. So for example, mean sea level is here. In a day, we see high tide and low tide. And then when we have a storm surge, we get what I call still water level. But if we get waves, if we get wind on that day, we will see some wave effects, and that causes some wave run up. So essentially, what sea level rise will do, it will basically push everything upwards. So all these nice, beautiful houses on the shoreline will be exposed to coastal flooding. The results, so we did some analysis back in 2012, I think. The city conducted a thorough, comprehensive assessment of coastal flood hazard, and that gave us this flood map, or designated flood map, which basically shows area where there's a high flood hazard. And this is based on 500-year coastal event that includes storm surge and sea level rise. This area that I highlighted is what we call Falls Creek here. Those who have been to Vancouver, you would recognize the Science World buildings right here. This was all used to be, naturalized area, but then urbanization led to dump of a lot of waste and like materials, and that's a consequence of it. So water has to find its way. As I said, it definitely found its way, and then there are lots of residential, industrial buildings in this area which are exposed, and the total value is about $30 billion at the time of assessment. So this was the journey till 2020. So we did some coastal flood mapping, risk assessment, and flood policy update. By flood policy update, I mean updating the building bylaw to account for flood construction level, which means the minimum elevation at which the habitable space has to be at in the designated floodplain areas. So in 2018 to 2020, we focused on selected floodplains. So we focused on Fraser River floodplain, Falls Creek floodplains, and we developed what we call adaptation plans. And that has been an ongoing journey, right? It doesn't stop there. It's not a 2-year work. It keeps on moving. There's so many dynamic factors in place. So we also did some investigation in other parts of the city, and also updated our shoreline flood protection engineering design reference. All in all, if there was one common trend, the joint impact of rainfall and coastal water level was not studied. And the reason it's important is because some of these floodplains, if I go back a little bit, they've got an urban upstream watershed. So for example, this area right here, this is a coastal floodplain, but then rainfall from this area also comes down. So this lowland has an upland contributing catchment area. So if there's a high rainfall occurring at high tide, that is like more severe to us from engineering point of view, right? Rather than just focusing on coastal flood only or rainfall at low tide, so and so. So that sort of thinking was not there, or like was not studied, I should say. But then this gave us opportunity for moving onwards, like these interesting projects that we were doing. We were investigating the compound events, moving onwards. So this is just another simple graphic that highlights why this is important. So for example, during a light rainfall event, water captured by sewers and catch basins find its way to the ocean body during a low tide, so it can discharge freely. But then when there's a high tide and also there's some rain happening, the discharge gets blocked essentially because of the high tide. And so water gets backed up, and water has to find its way through the catch basins because they don't have any backwater preventer walls. And this assumes there's no tide gate, which means that there's an actual infrastructure which is installed in the outfalls that actually blocks the tide coming in, but can be opened during the low tide. So if there's no tide gate, if there's no backwater preventers, water finds its way in pools here. And if you build a dike, a coastal flood protection infrastructure, you are essentially creating problems here because water will just be pooled behind the dike, right? And that's what we call, we don't want maladaptation. And that's why it's important to assess the combination of these two. I think if you are now getting it, why it's so important to assess the compound events. So we did a lot of different areas of the cities, different contexts. We did different investigations internally, and these two, perhaps I would say the main ones. The C2CD design challenge. There's a lot of useful information online, Vancouver.ca. Feel free to search this word C2City, and you'll find lots of interesting reports. It's all published there. So in these two projects, we investigated the joint combinations of rainfall and coastal and how it informed our adaptation actions. Today's presentation will be focused on this one. This we concluded early last year, if I can recall. But then conclusion doesn't mean anything. I'll say in the last slide. There's always continuous work towards implementation. So I think we're good time-wise. For this section, as I said, I'll talk about this case study. So this is the focus area. This is Fraser River. This is the south of Vancouver, by the way. This is south of Vancouver. This is Fraser River, and ocean is somewhere here. So this area is, as I said, vulnerable to coastal and internal drainage flooding because this area also receives rainwater from the upland watershed. There's no coastal flood protection here, like no dikes, no pump stations as of now. We have unfortunately destroyed or buried the creeks, so which means that we don't have enough conveyance capacity and under extreme rainfall events. There's limited land tenure along the shoreline. Actually, we don't even own any of these lands. We only own some of the outfall related lands. So that complicates our assessment, our approach as well, because if we don't own any lands, where do we place the pump station? Where do we build the dike, right? So that's a very complicated situation for us. And this area also hosts a lot of industrial lands, very valuable industrial lands, and also some residential properties. In fact, my office is somewhere right here on the floodplain. So it also has critical infrastructure. It has regional pump station, wastewater pump station, city works yard, electric substation, transit center is also coming up. So a lot of critical facilities on the floodplain. So now I'll start my discussion by also igniting some of your curiosity. So, for example, if a case study like this comes in your hand, so how would you start the assessment approach, right? So there's no like fixed template that goes always. For example, in this study, we decided that we needed a 1D 2D hydraulic model, and I'll explain later like why we needed that. Um, I hope with this course you are familiar of hydraulic modeling and may not be very specific in urban context, but the general essence of I hope you understand that. So we needed that modeling. One dimensional, two dimensional is basically one dimensional is where you only know what's going through the sewers, but you don't know what comes out of the sewers and where the water will find its way. So basically the flow of water on the surface, you don't know that. But with the 1D and 2D integrated model, you would actually be able to simulate the whole dynamics of it. So we needed that sort of model that has this flexibility. We needed to assess different combinations of rainfall and coastal water levels, i.e. the joint probability of these two events occurring together. Then we needed to assess the coastal flood protection and drainage infrastructure. So basically, you assess the hazard, you know what is basically what nature can cause to you, essentially in simple words. And then you do your consequence assessment, which means you understand what the damages will be if an hazard comes. And then because your hazard is probabilistic in nature, you know the risk, probability times the damage. So ultimately, its decision is solely relied on the risk in the end. And then you use that information to actually tweak the model, to tweak your scientific thinking, your technical thinking, to come up with some solutions and how you can lower or reduce the risk to a certain level where you can actually manage it with public taxpayer money. Also, we need to develop conceptual designs, like what kind of alignments we're talking about, what kind of land raising, street raising, pump station locations, and new outfalls. So like what does it include in terms of design and cost estimate? This is just like a basic stats 101 to give you a bit of context of dependence and independent events. So fully dependent event of two events, X and Y, the probability is same, right? Because they both are fully dependent. Fully independent, it's simply a multiplication of two, right? But then here situation gets very difficult when they are partially dependent. You might be familiar of this Bayes theorem, but it's more complicated than this. It's not just about throwing a dice and watching a coin and all of that, high school crap. It's not that. It's really very complicated when it comes to the joint probability of two random variables. So we start off by looking into, okay, let's look into some of the recent past events and see if there is any correlation at all qualitatively between the storm surge and the atmospheric river or simply the rainfall and the coastal water level. So I'll talk about two events. December 10th is an example of internal drainage flooding because of the backwatering of drainage infrastructure. And then December 27th is when a severe storm surge impacted the city. This is December 10th. So what you're seeing on the screen is in the black is what the predicted tides are. And in blue is what the tide gauge station observed on that day. And in red, you're seeing essentially the difference of the two, predicted minus observed minus predicted. So as you can see, the resultant is basically the surge, the extra increase in the water level. Right, so the peak surge happened, about 0.6, although the peak was here as well. So it sort of like plateaus for this period of time and then starts dropping down gradually. And then when we included the rainfall, we also found that there was some rainfall there during the same period as well. Although there was a little bit of showers, there was some continuous rain and then again dropped. So in about 18 millimeter over 96 hours, which is very small in our context, this is not a significant event, but definitely the two meteorological conditions, in some sense, they have the same driving factor, right? And let's say December 27th. So Again, you're in the black, you're seeing the predictions. Red, you're seeing observations. The difference between the two is here, the surge. Um, the max surge happened at this time, again, somewhat, coinciding at the high tide. So I should also highlight that it's not necessarily that always the surge comes at the high tide. The maximum surge could be at even the low tide. But then this is favorable to us because it's not going to cause any flooding to us, right? So it definitely, at what time the surge comes, it matters to us. And then when we plotted the rainfall, we saw that there was like continuous rainfall earlier, then we dropped, and then again picked up, and then picked up for a while, and then slowly damped down. So definitely we see some like, yeah, qualitatively, at least I can say that there is some correlation here, right? So before commencing the study, we investigated some of the background materials. This one is I like the most, honestly. This is the work done by Environment Agency in the UK. If I have excited you enough about this topic, definitely give it a read. You'll find tons of useful information in these three reports. Seriously crazy amount of work that people have done, and it's very impressive, highly impressive. So they analyzed for the entire UK, they analyzed different variables for dependence. So for example, they analyzed wave height and sea level. So, and like, does wave height has any correlation with sea level or not? Wave height and surge, tides and surge, daily river flow and surge, precipitation surge, hourly precipitation and sea level, wind, sea, and swell. So there are different ways of how you can represent the same variable, right? So you can have like hourly precipitation, or you can have daily precipitation. You can compare the sea level directly, or you can compare the surge only, which is the difference between the observed and predictions. So they investigated all of this, and there's like heavy bit of stats involved. Those who love it, check it out. But there are other projects as well. I think the list needs to be updated. But if I can recall, at that time when I analyzed, there were three main projects that I could find. The Thames Estuary 2100 was a massive undertaking, again in the UK. There is a EU flood site project. They have got a dedicated site. Check it out. Has lots of good information. Australia rainfall and runoff. They also investigated the compound events. There's a bit of local trend as well here in BC. One of the report was Squamish IFHMP. I always forget what this acronym means. Essentially, it was about flood protection. But this was not applied to urban drainage, right? So when we were commencing the study, we were not able to find any local study focusing on the urban context, and that too focusing on rainfall and coastal water levels.
Akhil, isn't it FIMP, Flood Hazard Identification and Mapping Program of NRCan?
That's an Arcan program, but
Okay.
I think the letters are same, but it's a different one. It's the one organized by the local government of Squamish.
Uh-huh.
Yeah, I'm not sure if they got funding from NRCan though or not, but yeah, it's different. FIMP is different.
Mhm.
Moving on quickly, I won't spend too much time on this slide, but just to give you a sneak peek of what the Environment Agency report provided, they provided this beautiful map, which actually showing you the correlation factor, the dependency map between rainfall and sea level. So basically, the green, from green to this color, it's basically the increasing level of dependence. And you can see that on this side, on the eastern shore of the UK, there's like low dependence between rainfall and sea level. But as we move west and south, we see increasing amount of correlation here, which can be attributed to a lot of different meteorological conditions of how this, geography is exposed to wind and rainfall events and tides. And the report also provided like three different measures how we can quantify the dependence, right? So it's in simple words, you can think of correlation coefficient between two variables. Chi, I don't know what the heck it means, but apparently it's a statistical term. You can also use it for some quantification of the dependence. Correlation factor is another word. So it's basically the actual frequency of occurrence of a particular joint event divided by the probability of occurrence of the two variables if they were independent. So in simple words, joint probability divided by marginal probability of one variable multiplied by marginal probability of another variable, right? So there are different ways you can structure it. That's another area of research if somebody is interested to pursue further. The study also gave you some like analytical tools, how you can, design infrastructure. Remember, like from all of this work, you need to design, you need to assess how your system is performing, and ultimately make recommendations on the design side. So this is where this report also provided a lot of added benefit. Yeah, I won't go into detail. There's like some steps here for analytical tools, and they also provided a desktop study, which basically simplifies a lot of work. So you can essentially use this lookup table. You know in what region you are in the UK. You know your variable one. So for example, variable one could be rainfall. So you know the return periods of the rainfall. Your variable two could be coastal water level. Depending upon the correlation factors, you know the corresponding return periods that you have to use to multiply and get the joint probability, and then use the joint probability to get the exceedance and the structure. And yeah, there's a whole lot of art to it, as I said. To visualize in graph, like what it means. So for example, this is just a demo for our case study I created. So for example, if I have a low correlation 0.2 value between rainfall and coastal water level, I get something like I get these contours. So for example, each contour means a different, a specific joint event probability. Right. So here we have joint 10-year, 25-year, 50-year, and so and so. And each point on this line is basically a combination of the two events. So a high rainfall and low coastal water level can have the same joint probability compared to a low rainfall and high coastal water level. So you get this like band of different events which are possible for a certain return period, joint return period. And when you have like a high correlation, so you see how the curve changes from like concave to convex, right? So there's like some statistical meaning to it. So when we started this study, we investigated some considerations. Like as I said, as I've been speaking, it really depends how you identify your variable of interest. So for example, you can represent 1 hour, the timing, for example. So do you want your coastal water level to be represented in hourly time step, or you want like every minute or 15 minute? And what about the rainfall? Does it have to be the both? Is it necessary that the both needs to be of the same time step? How do you align the peak? At what point you say that, well, there is a correlation, because they both are dynamic in nature, right? So the timing is another factor. How many years, for example, how many years of data you want to look. So that's another key variable. And all these are sensitive parameters ultimately. What statistical inference you're drawn from the set of data you have, it definitely matters a lot. What kind of dependence measure you are choosing. So for example, if you choose with CF value, or if you choose a correlation, you may end up different joint events. So which one is true what, right? What else? So like, yeah, you have like assessment criteria. So for example, let's say you get the joint event, but then how will you assess whether this joint event is actually causing any damage to your system or not? So what is the threshold, the deciding threshold? And how would you factor climate change? So your past historic data doesn't speak about the climate change. You can interpolate the sea level rise, but then that's not how it's supposed to be done. There's like whole range of plausible scenarios in future. So how would you factor in the changing climate conditions in joint probability? So joint probability of current climate conditions is different from joint probability of future climate conditions, right? In future, if there is more atmospheric river happening in Vancouver during high tides, that definitely increases the joint probability of these two events happening together. So there's a lot of thinking to it. I find this topic extremely intriguing still now. So I hope like I'm able to excite you about this as well. And then we started off by, so by the way, we hired WSP consultants on this study to run the models and do all the assessments. And we were providing guidance to them, like what to compare, what not to compare, because it was so new for all of us as well, right? So we started off by saying, okay, let's just plot the scatter plot. Easy, let's make life easy. Just plot the surge and the precipitation. But then we were like, oh, well, what about, like, what do you want? So like, do you want surge at the maximum coastal water level, or do you want to just use the observed coastal water level directly? So if you plot the surge versus precipitation, we got this like cloud of points, and we were like, well, how to interpret this? We don't see any direct correlation here. And then we were like, okay, let's just split it into different durations. Let's pick 24-hour duration, 12-hour duration, 6-hour duration. And does data say anything or not? So then we are like, oh, well, yeah, there is some slight trend in high duration, because the surge does not last for like 1 hour, 2 hour, right? It's an ocean condition that developed. So it typically lasts for like 6 hours or more, typically like 12 hours or more. It starts to ramp up and then slowly ramps down. And then we were like, well, we won't be designing our infrastructure based on the surge. We need coastal water level, because this is what we know what's going to happen, because based on the tides, right? So any infrastructure that we need to design is based on the coastal water level, the elevation of that. So we were like, okay, let's just observe the coastal water level and precipitation correlation. And this is where we got a little bit of different insights as well, right? So you can see the cloud pattern shifted a bit. I think there are some other nuances involved that also explains why there's a shift, but I'm not going to too much detail on this, just giving you some exposure that, hey, when you're working on these technical projects, you have to look into the whole spectrum. Like you have to be creative, like what you're looking for, what you're plotting, what you're inferring, and so and so. So yeah, I won't spend too much time on this slide, but then when we plotted the 24-hour, as I said, we saw some surge was present during the 24-hour storm event. So, but then we were like, well, it's not significant enough. Why? Because in Vancouver, the tides vary significantly. So in a day, we see like more than 4 meters of tidal variation. So it essentially draws down any effect of storm surge, because storm surge is like in the order of centimeters, right? 30 centimeter, 50 centimeter, 70 centimeter maximum. But then the tidal variations are so huge. When we create all these, hypothetical scenarios, we don't see the effect, coming out so much. And yeah, so ultimately what we concluded was that the observed coastal water levels in the rainfall were not sufficiently correlated. And so we decided that, well, let's just assume that they both are independent. And this is, done in like 2 years ago, right? So with new data, as we get new information, the probability distribution actually changes with the addition of new data, right? So it's a continuous process. 2 years down the road, if we do another study, we'll have to reinvestigate the joint probabilities, and we may find some new trends as well. And that's just the nature of the whole exercise, right? It's dynamic in nature. The whole system is changing. So yeah, so we ultimately decided that independent assumption would apply, but then we were like, okay, so we know the marginal probabilities, we know the return periods of the rainfall based on the IDFs, and then we can do a similar extreme value analysis for coastal water levels, so we can get the annual exceedance probability, right? So what is the probability of any variable increasing a certain magnitude at least once a year, right? That's the annual exceedance probability. So we know we can get the annual exceedance for both. But then does rainfall AEP times coastal AEP equal to joint AEP? Well, no. If joint AEP is something very different. So I'll try to explain here. So for example, if you take 1 in 10 year 1 hour duration rainfall AEP, and then you multiply it by 1 in 10 year coastal AEP, so it's not equal to 0.01 AEP, because in rainfall you have the duration in place. So you're saying that I have this 1 hour duration, of the rainfall with 10% chance of happening. Whereas my coastal AEP is represented at annual exceedance. It's not 1 hour exceedance, it's not 6 hour exceedance. So what we realized is that, well, we need coastal water level for a given exceedance durations. So we needed like what is the probability of coastal water level exceeding certain magnitude in 1 hour, in 6 hour, 12 hour, 24 hour, so and so. So that's how we ended up in having like these kind of tables that actually show the joint exceedance probability up at the top, and then for each combination we have coastal water level probability, rainfall probability, corresponding rainfall probability, and so and so. And so as you can see here, like different combinations exist that can give you the same joint AEP, and this is for one duration, which is here I'm showing you 12 hours. So we have one table for 24 hour, one for 6 hour, so and so, right? So now for us engineers, actually now it makes life a bit easier for us, because now we have this lookup table. We can run different scenarios, all of these scenarios in the model, hydraulic model, and we can find which one is a governing scenario, which means which one produces the largest, the highest water depth or total volume or peak flow, whatever is your criteria. And then you can focus on that particular event only for designing an infrastructure. There's a lot going on here. I understand. Even I'm a little bit tired in explaining, but it's just the nature of the work, And for example, here, the temporal pattern. So like how you want to set the temporal pattern of the tides, right? So for example, the November 14th, 2021 tide, which actually caused a lot of like billions of dollars of damage in BC. On that day, the tides were something like this. So the model would start at high tide. The model will see a low tide somewhere in between, then again a slightly higher tide, then again a low tide, and then again a very, very high tide in the end. So where do you want to assign the rainfall, essentially, right? So that's another question for us to figure it out. Do you want to have the peak of the rainfall at the high tide, at the near about the end of the high tide, or do you want to have the peak of the flow aligning with the high tide, because there is a gap between the peak of the rainfall and the peak of the runoff, right? So there's some subtle differences in there, like how you want to adjust, how you want to set up the hydrodynamic model is another art to it. So yeah, we built this model for this area. As I said, the focus area was this one, but then the contributing upland watershed extends way up. And so we had to include all the sewers and all the drainage infrastructure here. Essentially, water comes here, it's collected by all these regional trunk sewers. And so at these intersection, this one and this one, low flow is sent to west to this pipe, which goes to wastewater treatment for treatment. And then here, any excess during the rainfall event, it goes to the ocean. And this is what we categorize as combined sewer inflow. So all of that was modeled in the hydrodynamic model. And then I think this video is just to give you a sneak peek of the 1D, 2D nature. So for example, the rain just occurred. All these blue dots are showing you the flooded manholes, the nodes, and then these lines are actually showing you the flow path, overland flow path. And then ultimately we know, okay, where water sits, where water pools. And then as capacity is regenerated during the low tide, we see capacity regenerated in our pipes. And where we see some bottlenecks, the pipes are in red color. So we know, okay, where the targeted areas are for us to focus on. And this is the rainfall event simulation. For example, we can do the same for coastal. So in a few minutes, you will see coastal water rising up. This is no rainfall, just coastal water. So coastal water rising up. There are no tide gates here at the outfall, so it's causing backup. And you will see the color will change from like orange to red slowly as the water starts popping out, because there is coastal water level coming in, and then it starts ponding here, starts impacting the properties nearby. And you can see the extent of the coastal water level. It's all floodplain. So and eventually you will see as the tide goes down, the capacity is recreated, water can be discharged by gravity. And so the extent of the flooding goes down. Pipes are, getting back to the orange, to the red color slowly and slowly. But then at the end of the simulation, we'll probably know, okay, where where the floodwater pools eventually, and during the peak of the event, we also know, okay, what's the max exposure that can happen. So yeah, slowly coming to the low tide conditions and getting back the capacity. Yeah, we use this information in designing adaptation infrastructures. So for example, in the lowlands, we can embed the thinking of living with water. And I won't spend too much time on this because this deserves another talk. But then how you can raise the land, how you can flood proof the buildings, how you can, maybe build a dike or have like more naturalized floodplain for people to enjoy, connect with the nature, or you can actually host the water, accommodate. It's more commonly called in language. So you can actually design some facilities that can be flooded during high events. So this is, for example, this high tide, the storm surge levels. So we are designing infrastructure which is resilient, but it's expected to get flooded and absorb some water. Raising streets, making super dikes, basically increasing the whole land up to the flood constriction level. So it essentially acts as a dike. So there are different actions, different adaptation actions you can take. And yeah, a lot of coordination with internal groups, transportation folks, streets design, planning, you name it. Like you have to coordinate with all these folks, developing the adaptation pathways and identifying the policies, bylaws to enable the implementation, and then do all the design. The life goes on. In city, the project never ends really because it's a long process to implement any project. I think I would end here, but I would end here on this very last slide because someone asked me to provide some of the general insights for students. And I think if I reflect back my 6 to 8 years of career, I think these were some of the most relevant points I could find. So I'll go through them. In a sense, practical solutions really have simple situations, sorry. You would assume that, for example, this study that I was just talking you, we would, at the start, we didn't anticipate that this would take so much of a time and effort in developing our thinking of the joint probabilities and in how you can set up the model and so and so. So it may seem very simple that, yeah, you're designing, pump stations and dikes and all of that, but then it's really complicated in the end. And you got you be up to date with industry and academia, right? So I tend to also read papers published on Nature and WRR because I need to be aware of, okay, what's the new projections, what the new statistical tool out there that can help me with my job. And if you are aware of like what's happening in industry and academia, you'll be more confident in what you're doing and what you're speaking also. Collaboration, as I said, is really the key, right? So strong communication, I cannot emphasize more really. You have to have very good oral and written. I've seen worst of the worst presentations, worst of the worst technical memorandums written by consultants in my work history. And, it doesn't look good at all. If you cannot explain to your audience what you're intending to propose or doing, it doesn't mean anything. Whatever knowledge you may have, if you have to be very good in communication skills. So as you move on to your career path, whatever option you choose, definitely I'm trying to emphasize on this point. Yeah, balancing the theory and practice lead better problem solving, right? So I explained this earlier. And then learn to work with uncertainty, incomplete data. I think someone also touched on uncertainty analysis in this course, and that's definitely a very valued asset that he has given you. So, in our case, in our day-to-day life, we don't have the complete ideal data set to work with. We have to manage and we have to make decisions worth of $1 million based on these uncertain data sets and understanding. So you got to know the tools and you got to know, okay, where you are making some like risk-based decisions and so and so. I should end now. Yeah, that's
Great.
all from my side. I'm happy to take some questions, although we are at time 1:05, but I'm happy to stay for 15, 20 minutes more.
Okay, great. Thank you very much, Akhil. That was really impressive. Excellent. First of all, I was very impressed to see that at the city level, what you do is just very similar to cutting edge research, but in real world practice, That's great. The kind of modeling work you do, the kind of probabilistic analysis, looking at marginal distributions and joint probabilities. And yeah, I have a lot of questions to ask you out of my personal curiosity, but I'm going to pass the opportunity to students for now. And I'm hoping to talk to you later extensively about these things. I want to make sure that those online can see us well. Yeah, so students, online, in person, who wants to go first? Akhil, please, just turn. Do you mind coming here, standing up so Akhil can see you?
Yes. Hello, my question is about the slide 31, the model you used, which model you used, and did you validate for your model? Yeah.
Did you validate the model, huh?
Yeah, thanks for this question. So yes, we used a pretty top-notch industry software. It's called InfoWorks ICM. ICM stands for Integrated Catchment Model. So essentially, it can model, river engineering related, setups, coastal rainfall in urban setups, in rural setups. So groundwater events. So it's one model that encompasses all the hydrological tools that you have, and it also allows you to run different modules, different hydrological modules even. It's a hydrodynamic model, so it's a 1D, 2D. It can also allow you to simulate what I was showing you, the 1D, 2D nature of the infrastructure. Calibration, yes, we did calibrate. The model has been calibrated. So calibration gets very tricky under extreme rainfall. And, there's so many variables, like you may have some anecdotal evidences. Okay, this is where I remember, the water get flooded a lot. So does model show that? Well, yeah, it shows that, but then model is saying 60 centimeter flood depth. Should I believe it? So you have to use some of your engineering sense to actually calibrate the model. You cannot, as I said, we won't have the ideal data always to calibrate the model. We did have some flow monitoring in our sewers, which means we actually know under like low to medium rainfall events how our sewers are conveying the flow. We know that. So as long as our model can actually capture that, we know that, okay, yes, we have some more confidence. But under extreme rainfall events, water floods everywhere. You saw from the simulation, right? So there's no point in calibrating, okay, here I measured 55 centimeter of depth, here I measured 85 centimeter of depth. It doesn't work like that. So somewhat you have to make some like quantitative, qualitative judgments to calibrate the model. And calibration is one thing, but you have to another do check. It's called validation, right? So you have to validate your calibrated model to see whether it's performing in new events. So like in AI industry, they call it training and validation. So it's sort of the same thinking here as well. So yeah, we did all of that.
Excellent.
I have a question online.
Okay, so we'll go online. Dardi, you go first, and Morgan in the room after.
Thank you, Dr. 𝗲𝗲𝗿, for bringing in Akhil, and thank you, Akhil, for your presentation. I really enjoyed it. I live in the Fraser Valley, so I know Vancouver very well.
Okay.
So I can relate to a lot of things that you're saying. Now, that being said, the first thing I would like to mention is I took a note here. Let me quickly pull it. In one of your slides, you plotted simulation versus observed water level tide. And what I personally noticed, and please correct me if I'm wrong, is it seems like your model underperforms somehow. It's almost always under what's the observation is. Do you guys, sorry, yeah.
No, it's not my model actually. It's the observation right from the gauge, the actual physical instrument that's actually recording the water levels.
Yeah.
So those are the observed ones.
Yeah.
The predictions are coming from astronomical tides. So there might be some uncertainty in like what the true tides will be next day, just because of the nature of the math. But then this whole set of uncertainty in like tiny waves even can actually fluctuate water surface, right? Like very local climate conditions can actually change water level conditions. So the observations that you saw was basically the actual water level meter installed at the shoreline, measuring the water levels. And the difference is, they attributed as a surge, as I said, and the surge is coming from the low pressure system. So yeah, like
Yeah.
we don't have a tide predicted. Well, we don't have coastal water level models, basically. We don't have predicted surge. That's what I wanted to say.
Okay, sounds good.
Yeah.
Well, then I'll keep my question then. And the second thing I wanted to mention is you mentioned atmospheric rivers coming from the Pacific Ocean and inward. Now, but also you mentioned the Fraser Valley, the Fraser River, sorry, the Fraser River in the south. Now, we all know when those atmospheric rivers they go over Vancouver, they move inward, and the water tower and the actual watershed for the Fraser River it's actually inward. Now, what happened when that flood, I mean when that atmospheric river move inward and go feed the watershed of the Fraser River? So how do you guys incorporate all those activities going on into your model?
Yeah. I expected this question. That's why I was laughing. But we investigated. Yeah, you raised a very good point. So let me just step back. So the Fraser River also contributes flow to our study area. The thing with this context is that we investigated up to what stretch of the Fraser River upstream does tides have any effect. So we know from the hydraulic model that that's actually a regional model developed by a consultancy. So we took that model and then we analyzed, okay, at what point in the Fraser River, upstream of the Fraser River, it's all tidal. So it's all governed by tidal conditions. It's the Fraser River flow, the Fraser River contribution doesn't make any big change here. It's just because of the nature of the geography.
The
So
backwater effect of the ocean.
yeah, exactly. So it's basically coastal water level impacting the Fraser River up and down, up and down. We investigated spring freshet scenarios. I didn't talk about this. So we did investigate the spring freshet, which is the snow melt, rapid snow melt we found that those were not governing scenarios, which means that the Fraser River levels during spring freshet were not high as the winter levels. So the winter levels dominated, and the winter levels are governed by tides and storm surge. So that's why that was ruled out, and so we didn't include the effect of atmospheric river going as far as inland, although it didn't actually go that far, to be very honest with you. Like the extent of the point at which the point up to which the Fraser River is all tidally influenced is far inward actually. So even up to that point, there won't be that much of an impact downstream. So that's how I would summarize it.
Yeah, thanks, Akhil. So, do you think he was first? Okay, 𝗪𝗁, you go ahead.
Hi, Akhil. It was a really nice presentation, and I could relate myself, although it was totally new, the coastal flood, because I did a similar but very basic flood mapping back in my undergrad. I was really concerned, like the climate change is real, and in your modeling, I could see the flood map considering the climate change and the sea rise level of 1 meter, and there was a significant area that in your model tells will get affected and 30 billion or something around. So yeah, the study shows climate change is being considered, but as a city of Vancouver, what you guys are like a prominent step that you're undertaking right now or something like that? Thank you.
Okay, thanks, 𝗪𝗁.
So your question is around the actions that we are taking, right? In a nutshell, yeah. So
yeah,
I mean, it's a very small question, but then the answer is too too long. The actions vary. The actions vary in different aspects. So, for example, in certain areas, well, first of all, we look into as I said, we look into the hazard. So what nature can cause. Then we look into the vulnerability or the consequences. So we try to understand what's the adaptive capacity of existing infrastructure. So you in certain areas, your area could be exposed to, let's say, 0.5 meter of coastal water level, but then if the building is above half a meter of that elevation, then that hazard is not impacting your building, right? So your building is actually having some adaptive capacity. Or for example, in areas where the residential, the habitable space is above the maximum elevation where the flood water can actually go. And the underground is basically the parquets. So although the parquets can actually get flooded severely, but then the residential damages can be limited, for example, right, in that sense. So you can actually have some pumps in the basement to pump out the water, or like store it temporarily, then release it. So there is like whole range of flexibility that infrastructure actually have, or may not have. In certain, so we look into case by case. We don't develop a comprehensive plan that, okay, let's just build a dike and solve our problem. No, we don't deal with that lens. We take portion by portion and we analyze, okay, how, well, first of all, how we can reduce the risk to a certain level which is manageable for us. And because it's public money, it's taxpayer money, we have to be very cautious about what sort of infrastructure plan we are dealing. So building a dike is billions of dollars of expensive investment over several years, right? And you have to maintain it. It's a very hard wall. It doesn't provide any ecological benefits, right? It also causes like some erosion issues, sediment issues. It's, you cannot touch and feel the water. Like you cannot have this, living with water abilities. So we try to analyze, okay, how maybe we can raise the entire land and then have a naturalized shoreline that provides some access, that provides some opportunities to grow some wetlands in that area. We look into, well, we have flood construction level, which means any new buildings built on the floodplain will have to be at certain elevation. So at least they're theoretically protected. But then the flood construction level doesn't apply to public roads, right? So what about road access during those events? And the road access are already getting disrupted by something called nuisance flooding or high tide flooding or sunny day flooding. It's like it's a sunny day, but then you see tidal water. Why? Because the water is high enough, it can actually cause flooding. So temporarily road closures have to be made. And so we look into all these aspects. Unfortunately, I don't have like one sentence answer, but then we look case by case. We look into different lenses, like can we accommodate water? Can we resist? Can we live with the water? So the C2CD design challenge provides you some like design guidelines, design briefs, and yeah, so all of
Yes,
that.
that was a $1 billion question.
That was more than that, I would say.
Yeah. Okay, we'll go to Morgan and Richard. I see your hands up.
Like, I'm not.
You're very generous. Okay, Richard, you want to go first now? Oh, okay. Poor internet connection. Yeah, he's connecting from Africa, so hopefully we'll get him back.
Okay.
So you go ahead.
Excellent. Thank you so much for the presentation. My name's Morgan, and I was just wondering, in your travels or even just in your upkeeping with the industry or academia, is there a city that deals with flood management mechanisms that you'd want to see Vancouver kind of follow after? Like, what are you seeing in the industry right now?
Yeah, there are like, sorry, I got distracted. You're saying like can you repeat that question? Sorry.
Of course. So I'm just wondering, is there a city that you've seen or read about that you would like to see Vancouver kind of base themselves off of?
Yeah, and the reason I got distracted is because every city has got its different challenges. If you, for example, the Delft and the Dutch thinking is very different. Let's not go to Dutch. So let's go to maybe Richmond, which is just the south of Vancouver. It's another city, another municipality. The geographical setup is very different. The governance is very different. It's a very flat city. Whereas Vancouver has like slopes, ridges, that pushes water from upland to lowlands. And when you have like a flat city, just like Richmond, they've got ditches because they need to store water. For them, storage is a big question. For us, is managing the runoff is the main question. So if you have, you have to So your thinking, your coastal adaptation or extreme rainfall adaptation thinking changes just because of the geography of the city. And then it also ties to your transportation network. Do you have abilities to connect the drainage infrastructure with the transportation infrastructure or not? It also ties to the land use development. So for example, if you have lots of industrial lands which are exposed and they do not have enough adaptive capacity, so then you might have to think about some hard solutions like raising the dike level or embankment. So in a nutshell, yeah, I've studied some cities, like there's some in BC, all the coastal cities are facing similar issues, similar challenges. Some cities may have a lot of public funds, like us. We are fortunate enough that we can generate enough money to be invested in these projects. But some cities unfortunately can't, just because there's not much public money coming in for these investments, and that they have to be dependent on grant applications. And when you're fighting for a limited amount of grant applications, you have to like very strategic what you are asking for. And sometimes you have to like scale down your proposed infrastructure just because of the nature of the economics, right? So you can't ask for like one, like I think just very recently city of Merit got I think $60 million worth of public grant to build the dikes, and that took them, I don't know, like 4 or 5 years to get there. And I'm sure the city folks and the consultants might probably have figured out, okay, how to manage, how to be strategic about the $60 million. What can you do with it? Like it has to be a very strategic investment. So all in all, yeah, it's very context dependent to your question. And unfortunately, there's no one template that fits all. And yeah, I would say that.
Of course. Thank you so much.
Yeah, and I think we are running over the time that you've already committed to us, Akhil. Maybe one last, okay, Joseph. And those online, I mean, is there anyone still wanting to ask questions? Okay,
Hi,
Joseph.
Akhil. Thanks very much for the presentation. My question is a follow-up question to what my colleague Akhil asked. He asked whether you validate your model. First, you calibrate your model and validate the model. And you said, yes, you do calibrate and validate the model. However, your astronomical tide prediction and the storm surge does not tally. Always, the observed goes higher than your astronomical tide prediction. So you said this is due to uncertainty. And I'm asking, what is the city of Vancouver, or what are you guys doing to reduce the level of uncertainty? Because if you would always predict the astronomical tides and the observations are always higher than what you are predicting and always causing distraction, then what is, in essence, the work you guys are doing? So I feel if there's an uncertainty, why don't you give us the range of uncertainty so that at least we know it's better to over predict than under predict, and we're having distraction or having castor effect on the people. So I'm asking, what are you guys doing in terms of reducing the uncertainty level to be able to protect the buildings and the people? Thank you very much.
Yeah, good question. So to answer that, couple of angles to that question. So for example, in terms of predictions of the surge or the predictions of the tide, I think 2 years ago or so, till then, there was an initiative led by a UBC professor, and this model, the model he prepared, like it would be used for predictions. And so we would get like a week ahead predictions of storm surges, and that predictions would change as and when the new information comes in. I think it used to be updated every 6 hours or so. So those were some of our tools back then to make some informed decisions. Okay, we expect the tide level to go up to 5 meters on Wednesday. So depending on the level, we would trigger the emergency response actions. So we have that in place. But I think from last 2 years onwards, this initiative has been at the hands of, I think it's an NRCan now. It's doing it. NRCan has taken the responsibility of setting up the prediction model for this region. And I think for the first 1 year it was under like a beta stage, but now the model has been more stabilized now, and they have done their own uncertainty analysis, all of that, to tweak the model. So we get some predictions from the NRCan model, and then we use it to make our own emergency informed decisions. For the long range investments, so like 80 years, 100 years from now on, like dikes or pump stations, something like that, we rely on like hindcast simulations. Consultants would take the historic storm surge and they would fit some probabilistic models to it. They would run like hypothetical scenarios, like 2,000 simulations. I don't know if you heard about Monte Carlo simulations, but like you would run a batch of simulations, and you found, okay, let's say like 100 out of 1,000 times you exceeded certain level at this point, so that informs you, okay, that this is the likelihood of water level exceeding in this area. So there are different ways. You can go with the like Monte Carlo route, or you can I think in the Atlantic coast, scientists have developed a storm surge prediction model. Unfortunately, in the Pacific coast, we don't have one yet. Maybe they're already working on it, but I'm not aware of any active model for storm surge only. So there are some, yeah. I mean, it's an art, to be honest. It's an art, but then the art is relying on the science. There's no perfect answer. No one else is perfect, right? So it has to be tweaked. It has to be updated with new set of information. And yeah, for us, just to summarize your question, for emergency responses, we rely on NRCan's predictions. For long range, we rely on the sea level rise, which is on the conservative side, 1 meter sea level. And we also have like storm surge component inbuilt. And then we have something called freeboard, which is like a safety factor. Civil engineers love safety factor. And that's our tool for adaptation to uncertainty to most extent. So we have that freeboard guidance from our regulatory agencies. I think I'm not missing any other angle, but yeah, that's.
Yes, that was a very comprehensive answer, Akhil. You know what? We have Richard back. I'm just mindful of your time, Akhil. Can you stay a few minutes more?
Yeah, maybe 5 minutes more.
Okay, thank you very much. That's very generous of you. Richard, good that we have you back. Go ahead.
Yeah, thank you very much. I'll be very quick. I wanted to just understand the interface, because there's very beautiful kind of solutions Akhil is trying to do, the modeling and then some of the solutions. But then what is the interface between your work and the communities? So, how do you interface? I've not heard about it so far. Thank you.
Yeah, and that's a very good angle too. So speaking of interface, Richard, not sure if you, maybe I have to reshare my slide deck, but in the last, there were like some sketches that were showing adaptation options. So like sketches showing, land raisings and, flood proofing, dry flood proofing, wet flood proofing of the buildings, and building dikes and reserving space for like shoreline access and so and so. So to your question, the bigger answer is we go by public engagement, and you're very right. We can't talk about InfoWorks ICM model directly to the public. They won't understand like what the heck you're talking about, right? So we try to dial down our technical language significantly for public, and our flood maps, when they become regulatory flood maps, we publish them on the website so people can actually read and analyze the flood hazard. Although it's very sensitive, we have to be extra cautious about what we are sharing. But for the designs, we go for like public engagement sessions where some of us will be there answering questions from the public and seeking some feedback as well, because our designs are informed by public. As simple as that. We can use our technical competency to draft the skeleton of it, but then where you want to put bits and pieces and tweaks and shoreline access, for example, people would prefer bench, for example, and you have to think about like accessibility and all of that. So there's a whole set of considerations that you have to consider. once we go with this public engagement route, we develop some like sketches of different options, and then you would ask them, okay, how would you rate this and this and this based on these values, and yeah, we use them to fine tune our designs. So yeah.
Excellent point. So I think it's time to wrap this up. Akhil, thank you very much. I want to personally thank you really for bringing this wealth
No
of
problem.
expertise to my classroom. And yeah, everyone, please join me in thanking Akhil for the wonderful presentation and answers to our questions.
Thank you.
Thank you. My pleasure.